Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A Chemistry Unit 3 potential questions for any Unit 3 paper. Let's begin with the first part. Here I began by talking about carrying out a phlegm test. You need to remember the details of how to carry out a phlegm test, including the process of cleaning. You need to know that you can use platinum wire, nichrome wire, or you could use a silica rod. We clean the wire with concentrated hydrochloric acid. Add a few drops of concentrated hydrochloric acid to a test tube containing the sample and mix it in order for the metal to dissolve. Then dip the wire into the sample and transfer to the non-luminous part of the flame and observe the color of the flame produced. Another common question can be asking about origin of color in a flame test. Remember that electrons absorb energy from the heat and they do transition to high energy levels. They then return to the ground state, and then a photon of light is emitted. This has a wavelength that corresponds to a specific color in the visible region of the electromagnetic spectrum, and that is going to be the color you observe. On this note, you need to remember that some cations have no flame color, and that is because the photons emitted do not correspond to any color, or the wavelength they possess does not correspond to any color in the visible region of the electromagnetic spectrum. Examples include magnesium as well as beryllium. So you need to remember the flame colors below. Remember lithium is red, sodium is yellow, potassium is lilac. Remember rubidium can be red or purple, cesium blue or violet. Beryllium has no color, magnesium has no color, calcium can be brick red, strontium can be crimson red, and barium can be apple green. Connecting to the flame test, it's a good idea that you understand how to test for the ammonium cation. To the sample that you suspect to have ammonium cation, you need to add sodium hydroxide and then warm. A gas is going to be evolved, and that turns damp red litmus paper into blue. The reason for warming here is this reaction will occur between ammonium cation and sodium hydroxide. However, ammonia gas is going to be produced, but it's going to be dissolved in the solution. So when you increase the temperature, it's going to come off as ammonia gas. And also, you will need to damp the red litmus paper, because if the litmus paper is not wet, then there will be no solution for the gas as well as the components within the litmus paper to react together. You can also put concentrated hydrochloric acid in a test tube and hold it towards the test tube that is evolving ammonia. HCl gas will come off the test tube that contains the concentrated hydrochloric acid, and together the ammonia gas as well as the HCl gas will meet or will combine and react to produce ammonium chloride, which will be observed as white smoke. You need to remember that ammonia is the only alkaline gas, at least for your level, that can be examined. Moving on to testing for gases. It is recommended that you remember testing for hydrogen. It makes a squeaky pop sound with a lighted splint. Carbon dioxide, this one turns lime water milky. For oxygen, it relights a glowing splint. Chlorine gas turns damp blue litmus paper red and then bleaches it. Or if you use damp red litmus paper, it will just bleach. Ammonia gas turns damp red litmus paper to blue, and then hydrogen chloride gas, of course, will react with ammonia gas to form white smoke, or it could turn damp blue litmus paper red, but of course this is going to be visible for any acidic gas. Let's go to testing for anions. The first one is a carbonate. To the sample you suspect to be a carbonate, add hydrochloric acid, and effervescence is going to be observed. A gas that turns lime water milky is going to be formed. So sometimes this question is connected to thermodecomposition of carbonates. And remember, carbonates that decompose are group 2 as well as lithium carbonates, and they do form carbon dioxide as well as metal oxides. When we go to nitrates, this is also carried out by thermodecomposition. If a gas that relights a glowing splint is formed along with brine fumes and a white solid, that will be oxygen gas as well as nitrogen dioxide, and that will show us that this is lithium nitrate or nitrates of group 2. And if a gas that relights a glowing splint is given off and no brine fumes, that will tell us there is no nitrogen dioxide, and therefore the decomposition is for the other group 1 nitrates, which is not lithium nitrate. Moving on to sulfates. A white precipitate forms when nitric acid is added to the sample followed by barium nitrate, or when hydrochloric acid is added followed by barium chloride. You need to learn how to write the ionic equation for this reaction, and they could ask you for the reason as to why they added the acid first for both methods. Addition of an acid is there to ensure that there is no carbonate that can confuse us to form a white precipitate, and then we make a conclusion that it was a sulfate when it actually was not. So adding an acid first rules out the possibility of presence of a carbonate, so that any white precipitate formed is only attributed to presence of a sulfate. When we go to hydrogen carbonate, here we react with acid to produce a gas that turns lime water milky. It can also go through thermodecomposition to produce a colorless liquid, which is going to be water, carbon dioxide, and a white solid, so this could be observed. Remember that water turns cobalt chloride paper from blue to pink, or it turns anhydrous copper to sulfate from white to blue. This can be attached to a reaction where it was a hydrogen carbonate anion. Moving on. Testing for halide ions. Here you need to add nitric acid followed by silver nitrate. If it's chloride, a white precipitate will form which dissolved if aqueous ammonia is added. And if it's a bromide, a chrome precipitate is going to form which does not dissolve on addition of dilute aqueous ammonia, but will dissolve when concentrated aqueous ammonia is added. If it's iodide, a yellow precipitate will be formed which does not dissolve if dilute aqueous ammonia or concentrated ammonia are added. For Unit 3, trends in thermodecomposition as well as trends in solubility can be used to decode an unknown cation as well as anion. To decode an unknown ionic compound, please remember the trends in thermodecomposition of group 1 and group 2 nitrates as well as carbonates. Remember the trends in solubility of group 2 hydroxides as well as sulfates. Remember, for hydroxides, magnesium hydroxide is insoluble while barium hydroxide is soluble, so solubility increases as we go down the group for group 2 hydroxides. However, for group 2 sulfates, magnesium sulfate is soluble while barium sulfate is insoluble, so solubility of group 2 sulfates decreases as you go down the group. When we talk about thermodecomposition of the nitrates as well as carbonates, of course, it becomes harder to decompose them as you go down the group. This is attributed to the size of the cation and the ability for polarization or to have a higher charge density to cause polarization in order to weaken the bonds that need to be broken. So as you go down the group, thermostability increases. You need to remember the reactions between halides and sulfuric acid, and this could be useful in decoding a halide existing in an unknown sample. Remember that when sulfuric acid reacts with chloride, misty fumes are going to be formed, and those are going to be HCl. When sulfuric acid reacts with bromide, misty fumes, which are HBr, as well as a colorless gas with a choking smell, which is sulfur dioxide, and the brown liquid, which is bromine. You could also say brown fumes. When sulfuric acid reacts with iodide, we will observe misty fumes, which is HI, a colorless gas with a choking smell, which is sulfur dioxide, a colorless gas with a rotten X smell, which is hydrogen sulfide, a gray solid or purple vapors, which is iodine, and a yellow solid, which is sulfur. I recommend that you visit disproportionation reactions between halogens with water, cold sodium hydroxide, as well as hot sodium hydroxide. They could also use cold potassium hydroxide or hot potassium hydroxide. Remember the setup for thermodecomposition of a metal carbonate. The metal carbonate is going to be set up in a test tube and is going to be heated. The gas produced could be collected if you want to measure the rate, or the gas produced could be passed through lime water and see if it turns it to be cloudy. They could ask you about hazard symbols, drawing them, their meanings, and safety precautions that must be taken in a lab while working with chemicals with specific hazards, as well as their meanings. In October 2022, Unit 3, students were asked to draw the hazard symbols, so please remember to draw those in the diamonds. They could give you data about an organic compound that is heated. This is combustion or a combustion reaction, and you know it produces carbon dioxide and water. The products from the reaction could be passed into silica gel, which is a drying agent, to remove water, and the soda lime to remove carbon dioxide. So from this experiment, we could find the mass of carbon dioxide as well as the mass of water produced. That means you can use the mass of carbon dioxide produced to find the mass of carbon, and you could use the mass of water produced to find the mass of hydrogen. Remember, the mass of oxygen will be the mass of the original organic compound minus the sum of the mass of carbon dioxide as well as hydrogen. So we can use that to determine the empirical formula of the organic compound. Please visit empirical formula calculations from reactions, like reactions of metal oxides with hydrogen. There is an example of an oxide of copper, where students were not told if it's copper 1 or copper 2, and that was reacted with hydrogen. You could be required to use the data given to find the mass of the metal or oxygen in order to find the empirical formula and then find out the metal oxide whether it's copper 1 or copper 2. They could also ask you to draw the setup for this experiment remember the metal is going to be inside a specific tube. Hydrogen gas is going to be passed into that tube. And then you're going to heat the metal as the hydrogen gas passes over the metal. And then to the other side towards the exit, the hydrogen gas has to be burnt off so that it does not accumulate in the lab. They could bring experiments of rates of reaction and volume of the gas produced. Remember some reactions about marble chips, which is calcium carbonate, reacting with HCl, and then carbon dioxide could be produced. Here they could give you data and ask you to draw some graphs in order to maybe explain or describe what is going on. Use an appropriate scale, write labels as well as units on the vertical and the horizontal axis, and make sure it is appropriately drawn. When we go to functional group tests, remember how to test for presence of OH group. This could be OH alcohol or OH carboxylic acid. Here you can use phosphorus pentachloride and you will observe misty fumes. Please remember to write the equation for this reaction. You could also use sodium. Here effervescence is going to be observed due to formation of hydrogen gas. Learn to write a balanced equation for this reaction. Another thing is testing for the carbon-carbon double bond. Here we use bromine water. The color of bromine water turns from brown to colorless, and this is the most recommended method. Although some people can use potassium manganate 7, where the color turns from purple to colorless. You need to remember that this reaction, I'm talking about the one with potassium manganate 7, it will produce diols if it reacts with carbon-carbon double bonds. I recommend that you revisit oxidation of alcohols using acidified potassium dichromate. Remember that primary alcohols can be oxidized to aldehydes or carboxylic acids depending on the conditions. If it's heating under reflux, then carboxylic acids are going to be produced. But if it's distillation with addition, then we're going to produce aldehydes. You also need to know that secondary alcohols can be converted into ketones. Going on to titration, you need to learn to label lab apparatus like a burette, a pipette, a volumetric flask, conical flask, beakers, and so on. And then you need to remember that you should correctly read a value at eye level below the meniscus. Remember that methyl orange is red in acidic and yellow in alkaline, while phenolphthalein is going to be colorless in acidic and pale pink in alkaline. You need to remember to calculate the titer value from the initial and the final reading. You need to know how to choose concordant results and calculating the mean titer. They could ask you questions about preparation of a standard solution. You need to mix a known mass of a sample with a small volume of the ionized water to dissolve the solid sample, and then using a funnel transfer the solution and the washings into a 250 cubic centimeter volumetric flask. You need to add the ionized water so the solution reaches the 250 cubic centimeter mark. Then stopper that volumetric flask and shake thoroughly to create a solution of uniform concentration. The solution you have created is a standard solution, meaning a solution whose concentration is accurately known. Now, how can we carry out a titration? Remember the apparatus we need are conical flask, a burette, a pipette, a wash bottle containing the ionized water, a white tile, as well as a small funnel. You need to rinse the conical flask with the ionized water, and then using a pipette with a pipette filler, rinse the pipette with the ionized water, and then rinse it with some of the solution that you're going to add into the conical flask. And then using a pipette filler or a pipette with a pipette filler, transfer 25 cubic centimeters of the solution into the conical flask. Here you need to add 2 to 3 drops of a suitable indicator, and then the next step is to rinse the burette with the ionized water and then with some of the solution you're going to add. Place the burette vertically positioned on a stand and on a flat surface. Then using a funnel, fill the burette with a standard solution and tap to ensure that no bubbles remain inside the burette. Open the burette tap to release some solution to ensure that the space between the tap and the tip has some liquid or some solution. Then wash the burette tip with the ionized water to remove any dripping solution and wipe it off. Record the initial burette reading in a table of results. Place the conical flask below the burette tip, leaving space for swirling, and place a white tile below the conical flask. That makes it easier for you to see the endpoint. So add standard solution to the conical flask until the indicator permanently changes color. Then record the final burette reading into the table of results. And calculate the titer value by subtracting the initial burette reading from the final burette reading. Empty the conical flask and wash it several times with the ionized water, and then repeat the titration at all similar conditions until concordant results are obtained. The next part is about dealing with titration results. Here you need to use the concordant results to calculate the average titer and use this in the calculations. So ensure to fully practice calculating number of moles, molar concentration, mass concentration, percentage yield, theoretical yield, percentage uncertainty, and everything to do with molar calculations. You need to remember uncertainty in lab apparatus. Like for a 50 centimeter cube burette is 0.05 or plus or minus 0.05. For 25 centimeter pipette is plus or minus 0.06. And a 250 centimeters cube volumetric flask is plus or minus 0.03. If a balance is to 1 decimal place, the uncertainty is plus or minus 0.05. And if it's 2 decimal places, it's plus or minus 0.005. If it's 3 decimal places, the uncertainty is plus or minus 0.0005. When we go to making an organic solution, remember the lab apparatus, like a round bottom flask, a pear-shaped flask, a steel head, a condenser, fractionating column, a receiver adapter, as well as a thermometer with its own adapter. You need to remember to draw and label the apparatus used in simple distillation, fractional distillation, distillation with addition, as well as heating under reflux. You need to remember to position the thermometer appropriately in simple distillation. The bulb of the thermometer should be positioned at the entrance of the condenser. Remember the heat source that is preferred is the electric heater because some of these organic compounds could be flammable. You need to position the condenser vertically with an open tap if it's heating under reflux, and the condenser should be slanting or tilted and connected to a receiver adapter if it's normal distillation. You need to know that the purpose of the receiver adapter is to prevent pressure buildup, and you need to know that anti-bumping granules are added to promote smooth boiling. When we go to purification of an organic liquid, it is carried out to remove a desired organic substance from any other substance in the mixture. So the choice of the solvent used depends on the fact that the added solvent should be immiscible with a solvent containing the desired organic product, and the desired organic product should have a higher solubility in the added solvent than in the reaction mixture. You need to place the mixture, meaning the reaction mixture and the solvent of choice, in a separating funnel, and they will form 2 layers, and then place a stopper in the neck of the funnel. Gently shake the funnel's contents and allow the contents to settle into 2 layers. Remove the stopper. This is going to prevent buildup of pressure, and then drain the lower layer into a separate flask and pour the upper layer into a separate flask. Add more solvent to the layer with the desired sample and repeat these steps at least 3 more times to ensure that the sample has been completely purified. One more thing to understand, the solvent of choice should be added in small portions than in a single large portion. This will allow for efficient separation. Also, the desired organic product can be separated from the solvent containing it using simple or fractional distillation. When we go to drying the organic liquid, remember that most organic liquids may contain inorganic impurities, or organic liquid could be soluble in water. So to the organic liquid, we need to add a suitable drying agent and then swirl. We leave the liquid to stand for some time. The anhydrous drying agent is usually powdery, but if it absorbs water, it becomes more crystalline. Once this is observed, add more drying agent until the added drying agent remains powdery, and that will be proof that the organic liquid is dry. Filter off the drying agent, or we can decant in order to obtain the dry liquid. Please revisit the separation of iodine from water into the cyclohexane layer using a separating funnel. The iodine moves from the water layer to the cyclohexane layer. Of course, you should know that iodine is more soluble in the organic solvent than in the aqueous solvent. The suitable drying agents we would have used in drying the organic liquid could be anhydrous calcium sulfate, anhydrous sodium sulfate, anhydrous magnesium sulfate, or anhydrous calcium chloride. However, anhydrous calcium chloride is not commonly used because it dissolves in alcohol and reacts with some other compounds. To test for purity of an organic liquid, we carry out boiling point determination using the apparatus for simple distillation. So if the boiling temperature is the same as that in the data booklet, then the organic liquid is pure. You need to remember that impurities raise the boiling temperature. The method of boiling point determination is not conclusive of purity since many compounds can have similar boiling points. Experiments and enthalpy change calculations, because these are also common in Unit 3. Common questions include the setup for enthalpy change of combustion, as well as neutralization. Here you need to remember the procedure, description, and the whole procedure, and they could ask you for the sources of errors. They can ask you for the measurements required to be made in each. Like in the enthalpy change of combustion, you need to measure the volume of water whose temperature is to be raised, and the initial and the final mass of the spirit burner and its contents. You also need to measure the initial and the final temperature of the water. In enthalpy change of neutralization, the initial temperature of the acid as well as the alkali are measured separately, and then you need to know the volume of the alkali as well as the acid. The final temperature of the mixture of the acid and alkali is also going to be determined. That is the solution after the reaction is done. Connecting to this, they could bring experimental graphs. If these are given, remember to draw the line of best fit through the results to get the temperature change from the graphical data. Here they can bring an investigation of enthalpy change of dissolution of ammonium chloride. In this case, sometimes a graph is drawn for you and the temperature decreases and then begins to slowly increase. Remember that this is an endothermic reaction and thus the temperature decreases. However, when the reaction is finished or when the reaction stops, the temperature begins to increase because heat transfer is occurring from the lab to the solution. They could also bring a question investigating the enthalpy change of reaction between copper sulfate and zinc. Remember that the reaction starts after zinc is added, and the temperature of the solution before or as zinc is added is going to be the initial temperature. So draw a line of best fit through the points when temperature decreases and connect the two when zinc is added to determine the final temperature. The difference between the initial and the final temperature is the temperature change. And some questions may require you to use that temperature change to calculate the Q. So remember, Q is equal to MC delta T, and then delta H is equal to negative Q over N if it's exothermic or Q over N if it's endothermic. Some questions may require you to use the Hess cycle and calculate enthalpy change of specific reactions, so please focus on that. When we go to mass spectrometry and molecular ion peaks, please remember the following mass to charge values and their corresponding possible ions. The one at 15, the one at 17, 28, 29, 31, 43, 45, and 57. Many students forget that at 31, so please make sure you do not forget that. Moving on to infrared spectra, remember to practice with wave number tables, and remember that compounds that have very similar peaks can be distinguished using the fingerprint region. Moving on to the last part here, I just put some experimental things that you can look at, and these are extracted from your textbook. I just put them here so that you can remember how to draw them. Common lab apparatus used in organic compounds. We have distillation with addition. We have heating under reflux. We have fractional distillation, as well as simple distillation. So this brings us to the end of this video for the Unit 3 Chemistry Potential Questions. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.